Alright, wrapping up the last part of section 1.8, and it says show that f is continuous. Again, guys, I want to warn you on the exam, I don't say show, I ask, is the function continuous? What does that mean? Show me that f of pi over 4 equal the limit as x approaches pi over 4 of f of x. And why am I saying that? Because I know sine is continuous everywhere. I know that cosine is continuous everywhere. They split them up at a point. So I need to know at that point if the limit from the left, limit from the right, and the y value match. I start off with f of pi over 4. Well, that is 1 over radical 2 or radical 2 over 2 rationalized. It exists. I take the limit as x approaches pi over 4 of f of x. Well, to do that, I need to take the limit from the left, limit as x approaches pi over 4. If I go from the left, well, this is x being the left. And I notice this is a trig function, and we said the shortcut applies. That's simply the sine of pi over 4, which is radical 2 over 2. I take the limit from the right. And from the right, this is x being bigger than. It's the cosine of x. This is also a trig. So I simply substitute the value in by using the shortcut. And I'll get radical 2 over 2. Well, I know the limit right here from what I got out of those two. I know that the limit equals radical 2 over 2. So, since the limit as x approaches pi over 4 of f of x equals radical 2 over 2, that would be this. Equals f of pi over 4. F is continuous on negative infinity to infinity. Again, I know that sine is continuous everywhere, cosine is continuous everywhere. The piecewise function, I want to make sure when they split them up or connect them, if the y values match at these points. Here's another problem. It says, find the numbers at which f is not continuous. At which of these numbers of f from the left, from the right, or neither? Okay, well, let's see how that works. Well, this is what we know, you guys. X squared plus 1 is a polynomial that's continuous everywhere. 3 minus x is a polynomial or a line. It's continuous everywhere. Radicals are continuous everywhere where they're defined. So what could go wrong? Well, it could go wrong at those split points. It could be at 1 and 4 things went wrong. So let's take x equal 1 for starters. X equal 1. If I take f of 1, f of 1, this is the included part. That is 1 squared plus 1, that is 2. Got it. Now, if I take the limit as x approaches 1 of f of x, and that's going to work by taking the limit as x approaches 1 from the left. If I run from the left, well, this is x being less than. So, if I plug the 1 in, and the reason I can do that, it's a polynomial, that'll be 2. Very good. If I take the limit as x approaches 1 from the right, this is x bigger than 1. I substitute the value in because that's a polynomial. I'll get 3 minus 1, which is 2. Hey, that works. So this limit equal 2. Therefore, what I concluded out of this and this, I know that f is continuous at 1. Now, let's try figure out what happened at 2. At 2, I want to figure out what f of 2 is. F of 2, I'm sorry, did I say 2? You know what I meant. When I say 2, I mean 4. F of 4. F of 4, this is including 4. And that would be, what? F of 4, it's included in there. That will be in the 3 minus 4. That is a negative 1. Alright. And now, again, same deal. We want to take the limit as x approaches 4 of f of x and see what that equal. Well, we take the limit as x approaches 4 from the left. 4 from the left, that has to be in there. 3 minus x. 3 minus 4 is a negative 1. That checks. And if we take the limit as x approaches 4 from the right, it has to be in radical x. And if I plug that in there, that's a 2. This limit does not exist. So my conclusion is that f is not continuous at x equal 4. And to sketch a graph, well, let's get that out of the way. A parabola less than or equal to 1. At 1, we are at 1. Something like this, and that's included. A line at 1, if I put 1 in there, I'll get a 2. 1, 1, 2. Ew, okay, my mistake. When I put 1, this is shifted 1 unit up. You guys say something. Just sitting there. Shifted 1 unit up, so it looks like this. Right? And at 1 we are at 2. That's not included. So the purple doesn't include it, or the pink, but the green does. And it has a slope of 1 down, 1 to the right. And when I plug in 4 plugged in there will give a negative 1. 1, 2, 3, 4, negative 1. It's that piece of the line. That doesn't look pretty. It's that piece of the line, and it's included on the right endpoint. And then when the radical comes in, we know what radicals look like, but it starts at 4. If I put a 4 in, I'll get a 2. 1, 2, 3, 4, 1, 2. So not like a straight line, more like a curve. So it's not that curvy, but I'm just making it like that so it doesn't look like a straight line. So here we know there is a disconnect and it's not continuous. Now one thing I want to mention, if I ask you if this is continuous or not on a test, you could never graph it and say look at the graph. You have to show me by definition. The graph is only to confirm, nothing more. Intermediate value theorem is a very important theorem. IVT, everybody knows what that is. It says suppose that f is continuous. That's a must. F is continuous on a closed interval from a to b. And let n be any y value between the endpoints, where the endpoints are not the same. Then there must be a value on the x-axis so that that y value is attained. Now let me give you a quick graph, really quick, make things simple. Let's say this is A and this is B. And let's say n is some y value. Now if I say f of A is right there and f of B is right there, and if you have a continuous function, you know, any graph, continuous, right? Something like that. They're saying if f is continuous, that's the condition, and there is a y value. The y value is between f of A and f of B. And this y value, they call it n. They say, if you trace it, guess what? The x that you choose will be between A and B. Now, we're going to modify that slightly for what we need, and it's going to make things a lot simpler. Instead of setting two things equal, instead of saying f of c equal n, we're going to say f of c minus n equals 0. What that means, I am going to take this graph and I'm going to subtract n from each of those. If I subtract n from this, that becomes a 0. The same graph. That will be n right there. It will be 0 now. And if I subtract n from that, that will be a point right there. And if I subtract n from this point, that would become So this point will shift down n units. This point will shift down n units, and this point will shift down n units. So f of a will be actually right there, and the graph will literally mimic just like what we had. That's supposed to be something like this. The difference between those two, if I could show that this is negative and this is positive, then by f being continuous, I know for sure that 0 is in there. I know 0 for sure is between a negative and a positive guaranteed. So that's how we're going to play this game. Every time I want to use the intermediate value theorem, if I want to use it directly, that's kind of a bit too much work. Instead, I will set 0 on one side. If f is continuous, guess what? That's all I have to do. Show that on one end it's positive, at the other end it's negative, and everybody's happy. So let's look at number 54 really quick and see how that works. It says use intermediate value theorem to show that there is one root, 1, 0 between those. Show that basically between 2 and 3 there is a point. Well, guess what? I'm going to take 2 over x, and it doesn't matter how you do this, whether you move this to the left or this to the right. And I'm going to call this function g. And I'm going to say, look, g is continuous on 2 to 3. How do I know that? Well, g is only not continuous at 0, right? Or negative, but that's not the case. And if I take g of 2, what's g of 2? That's 2 over 2 minus 2 plus radical 2. That is negative 1 plus radical 2. That is bigger than 0. And if I take g of 3, that is 2 over 3 minus 3 plus radical 3. That would be, this is negative 2/3. That will be all over 3 to negative 7/3 plus radical 3, right? And that would be negative. That's negative 2 and 1/3. And radical 3 is 1 point some. So I would say here, g of 2 is positive and g of 3 is negative. Let me just separate this part. Therefore, there must exist, that's the conclusion, there must exist, or there exists, a c in the open interval between 2 and 3 such that f of c equals 0. And what's, I am so sorry, g of c equals 0. And what's g of c? G of c is 2 over c minus c plus radical c. And if you move that to the right, you get 2 over c equal c minus radical c, which is what they want. And there it is, an official proof. Okay, another one of those. Don't underestimate this, you guys. You really need to get this. So here, if we say, well, let's take sine of x minus x squared plus x equals 0. Let this be f, since we're so stuck on f. Well, what's f of 1 before we begin? That's the sine of 1 minus 1 plus 1. That's the sine of 1. And I know sine of 1 is bigger than 0 because 1 radian is in quadrant 1. And in the first quadrant, all trig functions are positive. And if I take f of 2, that is the sine of 2 minus 4 plus 2. That is negative 2 plus the sine of 2. Since the biggest a sine could ever be is 1, this value is negative. Now I start by saying, well, look, f is continuous on the closed interval from 1 to 2. Actually, it's continuous everywhere. F of 1 is positive and f of 2 is negative. Then, therefore, there exists a c in the open interval between 1 and 2 such that f of c equals 0. I'm out of time, and there's the homework.